In Unit 7, we discussed simple harmonic motion, and simple harmonic motion is any time something is oscillating or repeating a pattern. So we had already looked at some things that were simple harmonic oscillators, but now we were just looking at them in a new way. So our 4 different examples of simple harmonic motion that we covered in this unit were circular motion, so anytime something goes around in a circle, it's repeating its pattern. Mass spring systems, which we had already kind of looked at in terms of Hooke's law and conservation of energy, but if I were to stretch a spring out, it oscillates back and forth, so that is something that repeats its pattern. Swinging pendulums, which we also looked at in terms of conservation of energy, as well as tension and strings and centripetal forces and things like that. And then waves was a new concept of simple harmonic motion that we introduced in detail in this unit. So anything that is undergoing simple harmonic motion or repeating a pattern is going to have both a period and a frequency. The period is the amount of time that it takes to complete one cycle of the oscillation or repeat one pattern. Frequency is the number of cycles or oscillations that happen per unit time. So they are inverse to one another, and the equations are that t, or the period, is equal to 1 over the frequency, or frequency is equal to 1 over the period. Now, if we look at the unit, period is a measurement of time, right? So the unit is seconds. And for frequency, the unit of measurement is 1 over seconds, because it's 1 over the period, or seconds to the negative 1. And so that is called hertz, right? So for circular motion, it's pretty obvious the amount of time to complete one revolution, right, is the period, or the amount of revolutions per second is the frequency, right? But then we also looked at new ways of figuring out, based on the construction of either a pendulum or a mass spring system, what the period of that device would be. So first we talked about pendulums, where the period of a pendulum is equal to 2 pi the square root of L over G. And this just makes a lot of sense because L is the length of the pendulum arm and G is acceleration due to gravity. So if we just think about it practically, if you have a really long pendulum arm, right, it's going to swing back and forth and take a lot more time. And if you have a really short one, it kind of goes back and forth really quickly, so the period would be smaller. And then the acceleration due to gravity talks about how things actually, the rate at which things fall, and that's really what a pendulum is doing, is it's falling back and forth. So gravity affects that as well. Just keep in mind that it's under square root symbol, so if you're going to take want to double something, you really have to quadruple the length. Now, also, something that's a little less intuitive is that the angle at which we swing the pendulum really doesn't matter for our purposes within AP Physics within a certain range. It really does, but for us, we can just assume that the angle is not going to impact the overall period of the pendulum. Now, in terms of mass spring systems, the equation is similar, but it is the 2 pi the square root of m over k, where m is the mass of the thing that's oscillating, k is the spring constant. So again, this makes a lot of sense if we think about it intuitively. If you pull a big heavy mass, it's going to oscillate back and forth a lot slower and be a greater time. And the spring constant is like the force, the restoring force of the spring. So the greater the force of that spring, the quicker it's going to snap back and oscillate back and forth. And again, the change in x, or the difference in the distance that you start it at, or that it's oscillating at, should not matter. So even if friction were causing it to slow down, the period should still stay the same. So what really ends up happening is it reduces the amount of force, which reduces the rate of acceleration. But when you pull it really far, there's a great force, so acceleration is quicker, but it has to move a greater distance to oscillate. If we oscillate it at a smaller distance, then the force is smaller, so the acceleration is slower, but it doesn't have to go quite as far. So the period of the mass spring system stays the same no matter what. All right, so then let's go ahead and start talking about the new concept, which was mechanical waves. So a mechanical wave requires a medium to move through. There are other kinds of waves that don't require medium, electromagnetic waves, but we just talk about mechanical waves in AP Physics 1. And mechanical waves then need to move through a medium, so it is either in a gas, a liquid, or a solid, right? And really, the movement of a wave is a transfer of energy through collisions of atoms. So a wave really isn't matter moving from one place to another, but it's energy moving from one place to another. And that energy moves with these collisions between the particles. So that is why mechanical waves move the fastest in solids, because the particles are really close together, so the transfer of energy can happen very quickly. Whereas for gases, the particles are pretty far apart, so it takes a little bit longer in order for the energy to transfer. So there's two types. We have compressional and transverse waves. Compressional, also known as longitudinal waves, are where the energy or the wave movement is parallel to the actual motion of the particles. So if I were to send a pulse down a slinky and push it straight this way, the slinky particles would bounce off of each other and move in that direction and, transmit the compression from one end of the slinky to the other, but the particles of the slinky would be moving parallel or in the same direction as the wave travel. A transverse wave is one where it's the opposite. So if I were to generate a pulse down a slinky where I moved it like this, and you see a wave move along like this, so that is where the energy is going to still move from left to right across my page. However, the particles of the slinky are moving like this rather than like this to pass the compression through space. So we do have mechanical waves that act in the same, in both these ways. So sound is an example of compressional or longitudinal waves, but then also we have transverse waves that are mechanical, like if I were to send a pulse down a string. So now we can take a look at our model of a transverse wave, and it actually allows us to define some different parts about the wave. So here's my wave right here. Right, and so some parts of the wave are the wavelength, right? So every harmonic oscillator has some cycle that it repeats. So the cycle of repetition or one cycle for a wave is down, back up to its original position, and then back down again, right? So up, down, and back, and then it starts repeating itself. So that cycle, or right there, is what we call the wavelength. That's also the distance between the two peaks of the wave, which is called the crest, or between the two valleys of the wave, which are called troughs. The height of the wave from this rest line is called the amplitude, and it really relates to the energy that the wave carries. Now keep in mind that all oscillators are going to mimic this pattern if we're going to look at them graphically. So I'm sure you remember doing a sine curve for a unit circle and seeing that it's like pi, 2 pi, 3/2 pi, I can't remember, right? So, but this sine wave actually mimics something as it moves around a circle, right? Same thing with a mass spring system or a pendulum system. So if I have the change in x over time, we're going to see that it goes minus x, plus x, minus x, plus x, and we're going to see exactly that same sort of sine curve for any sort of harmonic oscillator. All right, so for waves, they're going to transfer energy at some rate, so that energy is going to move some distance over time, and that is called the wave velocity, or the wave propagation, right? So the velocity is in meters per second, and it is equal to the wavelength times frequency. Remember, frequency is 1 over seconds, and this wavelength measurement is actually a length, so if I take meters times frequency, I'm going to get meters per second, which is the velocity. They're inverse of one another, so if we look at two waves here, you can see that this wave has a shorter wavelength, and therefore it has a higher frequency, and this one has a larger wavelength, and therefore it has a lower frequency. So energy relates to amplitude, but it also can relate to the frequency that the wave has. All right, so all waves have a series of different kinds of properties, and we'll talk about what they are and define them in terms of sound waves, but it applies to any kind of wave. So the first two wave properties occur when a wave encounters a new medium, right? So there's two different things that can happen at this boundary to the new medium. The waves can transmit, so that is when the wave will enter into the new medium or transfer energy into the new medium. Or they can reflect, which is when the wave would bounce back off of that boundary. Typically, when there is some sort of interaction between a boundary, both of these things happen in different amounts, just depending on what the boundary is like. For a fixed boundary, when something reflects, the wave actually inverts itself. For a non-fixed boundary, the wave remains upright as it bounces back into the medium from which it came. Now, another wave property is diffraction. This is just when waves bend around boundaries, and we don't really go too much into detail about them in AP Physics 1. We do talk about them more extensively in AP Physics 2 when we talk about light. The Doppler effect says that the frequency that is perceived is relative to the velocities, and that's the velocity of both the emitter and the perceiver. So if you have a fire truck and it's driving with some velocity at you, it's going to cause the frequency of the wave that is being produced by the siren to get smushed up between you, the observer, and hear the truck that's moving at you, making you hear a higher frequency. If the truck were moving away from you, then it essentially takes that wave and sort of just stretches it out so you perceive a lower frequency. And it's both relative to the velocity of the emitter, but also of the perceiver. So you could be running at the truck too, and that would impact the velocity. Now, when two waves encounter one another, they undergo something called interference. And the interference of two waves can be both constructive or destructive. So constructive is when the amplitudes of the waves add to one another, where destructive is when they cancel. And in terms of sound waves, constructive means that if the amplitude were to get greater, it actually gets louder, whereas destructive, they are going to subtract from one another and it would get quieter. Resonance is when two objects are vibrating at the same frequency, and because of that, there is a bunch of constructive interference, so it increases the amplitude of the wave. Every single substance is going to have its own natural frequency that it vibrates at. So particles, even in a solid, are vibrating in some sort of fixed position. So this is the whole idea of an opera singer singing and a note at the same frequency of the glass, and they shatter the glass, right? Because the amplitudes of the waves are going to increase. But where we really look at resonance in this class is in terms of musical instruments. So we use musical instruments, always have some sort of resonance chamber or resonance body that allow them to make the note ring out very loud. So we deal with either open columns and strings or closed columns. So an air column that is open on both ends is going to be open to the air on both sides, and this behaves the same as a string. So within the wave, within the air column, we trap a standing wave that is equivalent to 1/2 of the wavelength, right? So where we have a node on both of these ends. This is called the first harmonic or the fundamental frequency, where the length of the wave, or the length of the air column, is actually equivalent to 1/2 of the wavelength. For a closed air column, there is a closed end and an open end, so the air pressure is different. So at one end we have a node, and on the other end we have an antinode. So the length of a closed column for a first harmonic is equal to 1/4 of the wavelength. If we were to look at the second harmonic or the next harmonic, for this, it would be the second harmonic for an open column or a string, where we see a node on each end, and that's where the length would be equal to the wavelength. For a closed air column, we can't have a second harmonic because that would make it so there was a node on both ends, so we have to actually jump and only do odd numbers, which would be the third harmonic. So length is equal to 3/4 of the wavelength. If we want to solve for any velocity or wavelength or length for any harmonic, we can use either one of these equations, where F is the frequency, N is the harmonic number, and L is the length of the air column, right? And then V obviously would be the velocity of the sound. So there's one other thing that impacts the overall velocity on a string, and the frequency that is on a string, and that is the tension of the string. Now this equation isn't on your reference tables, but it can be used from time to time. And so this just says that the velocity on a string is equal to the square root of the tension of the string over the mass to length ratio. All right, I've run out of time, so that's it for simple harmonic motion, sound and waves, unit 7.